You're in it, Dave.
Do you have the fixed laser pointer?
I'll walk around and
Go to it.
I got one left.
Okay, everyone get a good stretching. This is gonna take a while. So, today I'm gonna be talking about Taylor Park rock glaciers, and that's rock glacier right there, exploring their control of the distribution, headwall influence, and maybe introducing a new idea of how to model the regression. And that's the development of an input versus output versus elevation rock glacier activity stats diagram. And that's a mouthful, but that'll make sense once we get there. So, we need to understand what a rock glacier is first. They're defined as a visible expression of cumulative deformation over time by the creep of ice and rock debris mixtures under permafrost conditions. Basically, a big slurry of rock and ice moving down a slope like honey. And this is an Italian mountain. That's a big rock glacier. There's one too. And that's CB right there. They're defined by how fast they flow, the amount of ice they have in them, the amount of debris they have in them, and the superficial topography. So you can see furrow and ridge complexes going throughout. And what I'm going to try and do is what most geology talks do. They say, I'm going to try and, like, no one knows anything about geology, and I'm eventually going to forget that, but I'm going to try to explain everything from as basic as possible and scale it up to what I'm working on now. So, within a rock glacier, they form in different ways. The first mode of formation is the glacier derived. And what happens, you have a glacier, cover it with debris, you raise the ELA, which is the equilibrium line altitude. Basically that means it's above the ELA, you have snow accumulating, it's below freezing average summer temp, below ELA, your summer temp is above freezing. So you raise your ELA, the melting of the glacier increases rockfall as you de-weight the headwall, puts a lot of rock on the glacier, and eventually it's enough rock to change the deformation style from glacial deformation to rock glacier deformation. And that's the first mode of formation. Second mode of formation is you have a talus-derived rock glacier, which is where your rock comes in first. So you have rock shedding off the headwall, creates a talus pile, and then you have snow or water incorporate into that mixture. And I'm going to try and talk about how we can differentiate those two input methods. Enters the rock mass, and then eventually you build up ice amount to where there's a point where you can have creep due to ice deformation. In these cases, here you need glaciation to occur before you have a rock glacier. Here you don't, but these often happen in paired glacial environments. And I'm going to make an argument that you need oversteepened headwalls by glaciers to produce any of these features. So, inside a rock glacier, you have two main layers. You have your ice-rich core, that's that mix of ice and rock, and then on top you have your boulders which insulate it. In a glacial core model, that center core is mainly ice. There's going to be till and clasts in it, but it's predominantly ice with a thick insulating layer on top. And then in the permafrost or talus or scree model, you have a much more even mixture of rock and ice lenses, creating the rock glacier. So the deformation style, in a glacier you're going to have a consistent increase in displacement as you go away from the base, but in a rock glacier you have these planes of shear, which are concentrated at zones of increased amounts of ice. So that could either be within the glacier or within these ice lenses. Shear is going to be in those shear planes, and also, in both these models, you're going to have till deformation causing basal shear and basal slip. So you can classify rock glaciers by their geometry, but what I have found is the most impactful way and useful from a resource management standpoint is classifying these things by their activity status. So an active rock glacier is considered to have ice and to be moving actively. An intact rock glacier has ice in it, but stopped moving. And then an extinct rock glacier has no ice and no movement. And extinct goes by relic or dead. I'll use like dying, which means becoming, it's not a good idea, becoming extinct as you move through the progression. And this is kind of weird separating these two because the definition of this is no creep, but all these are in the mountains, so all of them are on the slope, and gravity's doing its thing all the time. So it's kind of hard to differentiate what is gravitational deformation versus what is ice deformation. And the way to tell these apart is mainly on the topographic features. For these active rock glaciers, you have really steep, defined front crests, a differential weathering because it pushes down slope. You're exposing clasts at that front so they don't get weathered, there's no lichen. So in active, you have clear lichen, no lichen, and then in attack, it's just kind of lichened all over. And then your extinct rock glaciers, you can have trees growing in them because they've stopped moving, so vegetation's allowed to grow. And there's also depressed features, as you can see here. Once you melt that ice, the rocks collapse, and you see much more muddled superficial topography. So, you may ask, why do we care? And we have a good reason to care. So, As global warming progresses, we're seeing more of our high alpine regions transition from glacial to periglacial states. So loss of glaciers is really resulting in a loss of ice and a loss of water for a lot of communities. In parts of Southeast Asia, Himalayas, and parts of the Andes, South America, these communities are going to see a transition where their water resource is currently glacial and it will become coming from rock glaciers within the next century. And this is important because we have pretty huge population centers here, and rock glaciers and mountains, they're the biggest water towers in the world. We need to understand these things so we can plan for a more resilient future. And they're also on Mars. Here's a rock glacier on Mars. If you want to go to Mars and explore it, we have to figure out where the water is. So, and they're also like super cool. It's like this big mass of honey and rock, and it looks super dynamic, but it's all rock, it's just flowing down a mountain. They're also really useful if you understand which ones are active to find water easily when you're running up high. And the biggest issue is that we don't understand them that well at all. There's been some work, but not much. There's a paper published called Review in Hydrology of Rock Glaciers, whatever. Basically says the first thing we need to do to understand them is just make databases. Understand their geospatial characteristics and describe their activity status. So this summer I got funded by a Renew grant through the DOE to do just this for Taylor Park. Here's Taylor Park. Wisconsin down here, Taylor River. It's just the upper Taylor watershed. This huge area through the Sawatch and the Elks, and has a lot of rock glaciers. So before doing this, before going out into the field and surveying these things, I worked a lot in ArcPro and Google Earth to identify their locations. Here's the same rock glacier in Google Earth and ArcPro. And what I'm doing is I'm outlining the features and trying to predict their activity status. I'm using slope rasters in Google Earth, as I said, and I use this mapping to plan my field surveys, pick the locations where I can get the most bang for my buck. Like I wasn't wanting to go out and just do one rock glacier a day. I was trying to hit like 10, 15, 20 rock glaciers a day and make the most of my time. And I also did a lot of snow and water sampling, but we're going to talk about that next. So here are some pictures from the summer. That was in April. Me and a buddy went out and skied and got a snow sample, and it wasn't because of the amount of snow that fell that day. That is up by the Apostles. We're just out in the middle of nowhere. Here's camp for the night, and here's my field notebook. And what a typical day looked like was about 14 hours of work. I would get to camp, build a wind shelter, process water samples, go through notes, go to sleep, and wake back up. And if you're just alone out there, there's not much else to do than work. So you just kind of work all day, and it's a pretty easy office to spend a lot of time working. Super tiring, but I mean, it's kind of hilarious I got paid to do this. Really awesome. So when I was surveying, what was I looking for? I was measuring the sorting of rock glaciers like you would measure a sandstone, and then measuring the maximum average class size, and that was the indice I kind of made up as a quick way of just getting a rough class measurement. And what I would do to get this maximum average class size, I just pick the 10 biggest class, measure them, and take the average to get a representative sample of how big the rocks were in the rock glacier. I was also observing the topography and the morphology of the rock glaciers, looking for that differential weathering, steep fronts coming out of these, and that would help me determine if they were active or intact or extinct, just looking for signs of movement. I was also looking for rock type. I'll talk about this in a bit. Could have done this better. This is one thing I'm a little upset about, but that's okay. And then differential weathering, that's what I was saying. I was also looking for snow. You can see there's snow under these slopes, but that makes sense. It's under a slope that's shading the snow beneath it, and it's likely avalanche occurring, so it makes sense that snow's building up right here. Snow right there doesn't make much sense. It's out in the middle of the open, and I was using snow in weird places as evidence that the future of the snow is almost cooler. So snow in completely exposed areas is likely indicating that there's still ice in there, it's cooling the surface and allowing snow to stay longer. I was also looking for springs coming from out these features, and that's indicative of interstitial ice melt. And when I had the chance, I would sample these springs. So what all the snow and the spring sampling resulted in is a lot of samples that we're currently processing. The goal was to process all these samples doing stable isotope analysis. So when you compare the ratios of heavy oxygen isotopes to each other, to light, and then the heavy to light hydrogen isotopes. And what this could tell us is the source of interstitial ice, how old it is, and if it's coming from snow melt, refreeze, avalanching, all these different things could be understood by this. We were able to run a few of the samples, and they're looking pretty good. The results are agreeing with, there's one other published paper out right now doing the same thing from the Uintas and LaSalle's from 2023, and the results are agreeing with that. But then the Picaro broke, and we have how many? 120 left to go through. there's a lot to go through. But they're all there in the fridge, and they're just waiting to be worked on. So this was what I produced from the summer. This is step one of the paper as they were talking about, making this geodatabase. So what I have is a geodatabase of every rock glacier in Taylor Park. There's 178 total. 68 were active, 49 were intact, and 61 were extinct. I wasn't able to visit all of them, but I visited 142. So I visited a good amount to get a pretty accurate database. In this database, there's a description of the rock glacier feature. You'll be able to see it right there, and it just kind of shows defining features, what I use to classify it, a picture or two if there's a good picture to add, and then spring data is here, and you can click on the rock glacier, it comes up with all of its sorting, all of its activity status, all of its class size measurements, and right now this is living on the school G drive. So any school computer, you go to the G drive, Taylor Park folder, rock glacier folder, anyone can access this, anyone can play with it, it's pretty cool. Then I also have all the other weird gravel deposits in the high alpine, like moraines, landslides, provincial ramparts, protalus ramparts, and those two are really annoying to differentiate, but it's all there with a focus on rock glaciers. So there we go. That's step one of how to understand these things. That brings me to the fall. So summer, I collect all my data, clean my database, and now I have my data set to work with, about 10 weeks of work getting that data. Now we're looking at the controls of distribution. So the classical understanding of the distribution as seen in most studies, and here's a few that look at it. They're looking at the elevation of the rock glacier body, the mean annual air temp, which is MAT, aspect and insulation, and they're focusing all these on the rock glacier body itself. And they're finding, not surprisingly, that most rock glaciers and most active rock glaciers occur at high elevation, low air temp, north aspect. Ice is where it's cold, and that's not too surprising. Ice is where it's cold. But not many studies focus on the geology or the landscape geometry when describing the distribution. And that's a problem that we should probably find. Here are just a few of the papers. Is there one right here? Yeah, here's from the Colorado Front Range, a paper published in 2007. And it's just a compass rose showing the aspects with highest elevation in the center and lowest out. So like Navy rose, same type of visualization. And you're seeing that rock glacier right here. Those are active rock glaciers, centered in the centered and north aspect. And then here are glaciers, and then here are extinct rock glaciers, lower elevation, and less confined by aspect. This is a study in the Himalayas, looking at rock glacier distribution. Similar diagram here, and then that's just showing the distribution based off elevation, and you're seeing a clump of your most active at the highest elevation. And basically just confirming that the bodies of the rock glaciers themselves are where it's cold. I then took this and applied it to all my things. So you apply this classical understanding to Taylor Park, and it's kind of unsatisfying results. You get, these are just box plots with extinct, intact, and active, and then just looking at how those are distributed. You see your extincts are the lowest, intacts are the middle, and active are the highest. So that seems to be correlating with other research. And then I did the same aspect distribution, and it's kind of weird. You're seeing a huge clumping on the southwest. You're seeing the grouping of them at high elevation, but you're not seeing a clear separation based off aspect. And that's not too helpful when you're trying to understand where they're extinct, where they're active, where your ice is going to stay the longest, where your water resource for the people below is going to stay the longest. The reason I'm attributing like this huge clump in the southwest is kind of weird, and I try to figure out why that's happening. And what I think is going on here is you have a southwest dipping mountain front, and just if you dip the ground to the southwest, most things are going to flow to the southwest, no matter how they're situated. And that's just making a preferential flow direction of these aspects to the southwest. This is kind of a man-made problem, right? If you were to survey this whole rock glacier area, you'd probably get more evenly distributed distribution across aspect. And while this is a problem man-made, it's not a problem like we're going to see in other places. Imagine you have a country here, divided by a ridgeline, and they're trying to understand their water resources, and you do a survey of rock glaciers. And you only have one aspect to do on, and you're trying to differentiate between which are most active and which are least active. And you're looking at aspect, it's not that useful. So while here, it's kind of, it's not a real problem in the Swatch, but it could be in other places. And even if we could survey the whole side, we were seeing a clumping of them on the southwest, but we're seeing no differentiation between activity status based on aspect. And that's kind of unsatisfying to me, because all current literature is basing rock glacier distribution off elevation and aspect. So I just ran some simple correlation tests in R, upon my data set and looking to see what things are actually related. And we're getting that aspect, or that elevation is correlated, and it has a p-value that means it is statistically significant. So we have one, in the classical literature, one distribution characteristic that is meaningful. Aspect, bad correlation coefficient, bad p-value. The problem with aspect is that it's a circular data set. It means 360 and 0 equal the same, 359 and 1 degree are the same, so it's really hard for a computer to calculate correlation between those two things. So I'm using insolation as kind of the proxy for aspect. You can see here, insolation, not like how much like things are keeping your house warm. I'm talking about solar insolation, so the amount of energy of sun rays hitting the ground. You can see, or the way this calculation is being done is that it's looking at the aspect of the ground surface and how steep it is. So if things are really north and really steep, they're getting no sun, no solar energy, very low insolation. And you can see how close these are related to each other. So you would expect that higher insolation means warmer temperatures and less activity. And you're seeing no correlation or even like some positive, but so low to really even look into. It's really just saying that insolation and aspect of rock glacier body aren't too meaningful to how active they are. Also, one thing to note is that most studies, from what I can tell, it's not completely clear how they're measuring aspect, but I'm pretty sure they're going into Google Earth and just measuring with a ruler from the rooting zone of the rock glacier, so like where it meets the mountain to its toe, which seemed like a real pain to me to go over and measure each one, and it's totally prone to human error. Like if you just measure a little bit differently, you're gonna get different values. So what I've been doing is using Zenolstat's mean tool in ArcPro. Basically, it just takes your slope raster, and I'll explain that in the next slide, and just adds them all up and averages them. It's a little weird to figure out because you have to do a circular mean, not an actual mean, but this is a better way of calculating aspect. It's repeatable, it's not human error prone, and it's way quicker. You don't have to sit there with a ruler and measure 176 of these things. So, what we're getting at, what I'm trying to get at, is that the current way we are looking at rock glaciers isn't that good in Taylor Park and may not be that good overall in a global sense. And most of the literature, as I said, is looking at elevation, aspect, and insolation of the rock glacier body. And to me, that's only one half of the system. In a glacier, you have your ablation zone and your accumulation zone. And your accumulation zone is where you get all the snow to put into a glacier. It's like we've been looking at rock glaciers only from their ablation zone, only how they melt and how they degrade. I want to start looking at how they're being fed and how snow, rock, ice is getting put into these systems. And the head wall is what's responsible for this. It's responsible for the rock reaching the system, the amount of rock, which is the insulator, and the amount of snow. As I said, they've long been looked at as this like paleoclimate study, in which they definitely are, but they're looking at how they degrade, and I'm trying to look at how they're being fed as a control in the distribution. And yeah, that's just what I'm saying. Let's investigate the rock glacier distribution based off the geology and geomorphology of this head wall and how it affects snow transport, snow collection, rock transport, and rock volume into the rock glacier. And this is a photo from near North Apostles. I'm standing at an active rock glacier right here, and that's one down there as well. I'm about 1,000 feet above it. That's flowing to the southwest, that's flowing to the north. Everything would say that this one's more active and will survive longer. From my field surveying, this one had clear differential weathering, more sign of movement, and looked much more active. And that's where I got this whole idea. Here's two rock glaciers that go against the obvious trends, and it seems like this is happening a lot in Taylor Park. Let's try and quantify this, let's research it, and let's see what we can actually do. So, to do this investigation, the data I used was my field data set from the summer and a 1 meter DEM. That's it. I'm using no climate data, no geologic mapping data, just the shape of the landscapes and how that reflects paleoclimate, current climate, and rock transport. And the tools I used was ArcPro for mapping, ArcPy, which is a Python mapping package, and then also Python to iterate processing of my data sets, and then R for statistical analysis. Before I get any further, I need to explain what a 1 meter DEM is. So, the type of raster data set. Imagine this tiled floor is the earth, and you just overlay a grid on everything. You assign each tile of the earth a value. It could be aspect, it could be elevation, it could be vegetation, it could be anything you want. What a DEM is this tile data set, grid data set, that's parceling and categorizing the earth's surface by elevation. So, just you take a value and put it to a tile. So, higher elevation is going to have a higher value per tile, and what you can do, you can calculate slope, insulation, aspect, all these cool things just from a 1 meter DEM. 1 meter DEMs aren't incredibly common. They're common in the US, but not the world. That's one issue with this study. It's hard to scale to other places that haven't had this type of surveying yet. Eventually we'll get there, but 1 meter DEMs are pretty available in all North America, or US. So what I did is I spent all semester making all these different models and tool indices and lots of different ways of quantifying lithology and fracture spacing, avalanche potential, looking at snow volume, porosity effect, and did a ton of cool things. And then I ran one more model like 2 nights ago, and it nullified everything. And it came up with this way cooler and way more simplistic model that is able to synthesize all this further cool stuff. So there's a whole other presentation that got deleted on Wednesday night, and now it brings us here. So this is kind of wordy, but this is what the rest of it is about. The effect of area above n degree slope within an RG input net upon RG activity status, and this RG means rock glacier. Let's try and unpack that. So most papers are looking at just the head wall of a rock glacier, a directly oversteepened portion above the rock glacier. Here's a rock glacier, here's its head wall. I'm making a differentiation between input net and head wall. Input net is the whole hydrologic net that could contribute to the rock glacier. Not directly oversteepened, but it's a whole area. And what I'm trying to look at is how this whole system is being reflected down in the rock glacier through its activity and size and distribution. The first aspect, where am I? The first aspect of the head wall we need to look at, or what's supplying rock glacier, is rock and ice. And all that's coming from up here. So let's unpack that. The first part of the input net we need to research and try to understand is rock and rockfall. So there's the rock component. The volume of the rock reaching the rock glacier should be controlled by its lithology and strength. So this is what I was talking about, the issue in my survey. I have lithology on 142 of these, but I focused my lithology surveys on ability to beryllium 10 date, which would be super useful. We just never got to that, but someone else can do cosmogenic data on these, and what that could tell you is at what time these rocks were exposed. So what time they were released from the head wall and have been exposed to the sun. I can tell you which ones we can beryllium 10 date, but that means I would just call things a granite or a gneiss. I wouldn't differentiate a gneiss that's an amphibolit or a schist with lots of mica and biotite. As we know, those two things are going to have very different failure mechanisms. I'm getting away from the people who don't know geology, but just the rock surveying I did was great for dating, but isn't too useful for rock strength. And to quantify rock strength, I mean, if someone is really good climber and has no fear of heights and knows how to use a Schmidt hammer, if they just want to go climb on all these head walls and do full RQD, RMR indexes for all these, that'd be great. But I don't have that, so I'm not going to focus on lithology and rock strength. The thing is, Taylor Park is pretty uniform. There's a 30 million year old granite suite in here, and then some volcanics about 30 million years old, and then some limestone sedimentary stuff, but most of it's the Precambrian basement, gneiss, granite, hard stuff. So we're going to make the assumption that rock fall volume, not its ability to be transported, but the volume that will be released is relatively constant over Taylor Park. And that's a big assumption, and it's kind of hard to make, but it's the one I have to make with my current data. So we're assuming that the rock fall that could be released has the same potential to be released. We have to understand how it is going to be released, which is based off slope steepness. And this things make it a little conceptual. So we're looking at slope steepness in relation to the ability of a head wall to transport rock to a rock glacier system. We need to understand its frequency of failure and its volume of failure. The general idea is that steep slopes that are steep don't fail because they are steep. If they had fallen, you would see a head wall recession back, and you'd see the evidence of failure. So if your slope is too steep, it's too strong to fail, and thus hasn't failed that often. So we're looking for a slope that's above its angle of repose, so it still has the potential to fail, but not too steep, indicating it's too strong that it hasn't failed. Now about volume. If your slope's too steep, your rock class will weather off, and the second they weather, they're going to be transported down the slope. If you have a slope that is closer or below even the angle of repose of that lithology, it allows rocks to weather off, become loose, and build up and accumulate on the slope before the complete failure. And then let's say you have something that increases pore porosity. You just have big rainfall, big snow melt, and it's a massive failure of rock. And that could be important because you need a lot of volume to insulate. If you have snow on top of a rock glacier body, you don't really care if you have a pebble to go on top of the snow. You need rocks to release in large volume so they insulate the snow and protect it from the sun. So what this means is that we're looking for a mid-ground and slope that would produce the largest volume of rockfall as well as the greatest frequency of rockfall. And if not by snow incorporation, I'm talking about the volume per event. It's still, rockfall matters because it's incorporating the ice and percolating water that refreezes into the rock glaciers themselves. So that's understanding the rock component of headwalls. Let's look at, you don't take my word for it. Study in Switzerland looked at this too. You're seeing your flat slopes aren't failing really at all. That makes sense, they're flat. You're seeing your mid-ground, your steep slopes failing quite often. This is just looking at frequency, not volume. Your steep slopes are failing often, and then your cliffs over here, those two blues, don't fail that often. And that is just some data explaining that concept. So, we have an understanding of how rock, the lithology, strength, and steepness of the slope could affect how rock is delivered to the system. Now, let's try to figure out the ice component. So, you have to ask yourselves, did it reach the rock glacier by snow or ice, or by snow or water? And that's kind of hard to differentiate, but I think I have a way that's maybe a little pseudo-statistically looking at that, but it's an okay model. We can assume that water is being actively incorporated into functionally all rock glaciers, either currently or sometime in their past before they died and became extinct. Even in a glacial formation even in the glacial formation model of rock glaciers, you're having modern input of snow and ice into them. And if you didn't, you would see rock glaciers have like huge bergschrunds where they've moved away from their headwall slope, and you're not seeing that. I saw it in one rock glacier, but we can assume functionally all rock glaciers are having water put into them actively as well as rockfall. And if you talk about this in terms of slope, which I'm going to do, not right there. So if you're having snow enter your rock glacier system, the snow that falls on top of a rock glacier body will not be enough to sustain the rock glacier itself. If that snowfall on the rock glacier body itself was enough to accumulate, you likely wouldn't have a rock glacier, and snow would accumulate up and you'd have glacier form. You're not seeing yearly snowfall reach that amount. You're seeing avalanching, what I think, and Professor at University of Utah is thinking as well. You're seeing avalanching periodically that allows the rock glaciers to grow. Here's just an image of avalanche transport of snow, which some people may recognize that avalanche from last year. And here's a picture of wind transport, your two main transport methods of snow. If you're assuming that these are being fed by water, slope wouldn't be an issue. And all the water in the input net wouldn't reach the rock glacier. So what we can look at is, this. We can look at it based off steepness. If we're seeing avalanching as our main input method to rock glaciers, we should probably see that the rock glacier activity and size is quite closely related to the steep amount of area above it, that head wall. And if we're thinking that rock glacier activity size distribution is correlated to the amount of water entering the system and subsequently refreezing, you should see them more closely related to the amount of area total. But this is only looking at avalanching into a system. This isn't accounting for wind transport, which is also a huge way snow is moved in the high alpine. And I've tried for a while to make a lot of cool models and like figure out how you can predict where wind transports, and the answer's kind of been in front of me, and I was kind of annoying to realize. But if you look at wind transport over a slope, wind will pick up snow and move it from one side to the other. And this is the windward side and the leeward side. And what happens if you do this over a long enough period of time and cold enough climates is that you have snow accumulate on the depositional side, which will then cause glaciers and erosion and oversteepening. So what we can look at, we can use steepness of a slope as a proxy for wind loading. Slopes that are steep have likely been glaciated and are likely wind loaded. So not only does slope steepness tell us avalanche potential currently, it tells us the paleoclimate wind directions and the wind loading currently. So basically, steep slopes indicate avalanche movement of snow into rock glacier, as well as wind movement over ridges into the rock glaciers themselves. And we tell that because a long time ago there was more snow there than the other side, meaning it was wind loaded. That's a little contextual, but that's what we're doing. So that describes our methods of transport of rock and snow into a rock glacier system. And slope is the big determining factor for all those. Of course, you use climate data to tell snow volume, but transport potential is going to be told by steepness. And same thing for rockfall and rock frequency. Lithology and strength will tell you the volume, but the frequency and the volume of the frequency should be indicated by slope steepness. That brings me to this model. So you're looking for that medium ground of where your slope isn't too steep. Like a low slope is leading to higher rock avalanche volume, because it allows them to build up on the slope. And then high rockfall frequency, where you have steep slopes that are over-steepened and need to be brought down. And for your snow transport potential, if you have too flat of a slope, it's likely wind-scoured. Medium slope is wind-loaded, but it's below avalanching angle, and once you can start avalanches, your snow transport potential just increases quickly. And you may say, avalanches happen 30 to 45 degrees. Yes, that is true. That's because that's where slabs form. If we're talking about snow transport, by sloughing or avalanching, the higher the slope, simply the higher the snow movement potential. So yeah, we're not able to tell the actual volume, but if we assume that in Taylor Park that climatically it's relatively uniform. We know that in the Alps there's more water, more snow, and in the Swatch it's drier. Just assume it's relatively similar. Compared to Antarctica and the Atlantic Peninsula, precipitation values are pretty much the same in Taylor Park. And we're also assuming that our rock strength and lithology is close enough, because tectonically it's all the same region, that the rockfall volume potential is relatively uniform over Taylor Park. We can look at transport, how transport should affect rock glacier input. Any questions on this so far? Take a little break. Anything? That all made sense. That's crazy. So, basically, let's start looking at slope and how that can affect rock glacier growth. So, as I said, I take my 1 meter DM raster and you can make a slope raster out of it. And here's just, this won't mean much to most people, but if you know GIS, this will hopefully make sense. I took my 1 meter DEM and just made a slope out of it, and I took the raster calculator and found the slope greater than or equal to a certain slope value for n. N is binned in 5, so it's 0, 5, 10, up to 85. So now I have 16 rasters, I get 16, which is starting from slope above 0 to slope above 85. And I took the zonal stat sum of each of these per slope degree over the rock glacier input net area. And then I took these values, extracted it, put in an Excel spreadsheet, joined it all up in R, meshed it all together, and have the values here now tied to rock glacier body values themselves. And then I did all this in R and compared values to activity status. Here's what this analysis looks like in GIS. You're looking at slope greater than or equal to 0. All slope is above 0. So your whole area is given a value of 1. This is a 1, 0 raster. Red is 1, gray is 0. And then you iterate that for 0, 10, 20, 30, all the way up to 70, and you see it's a clear decrease in slope. You can see the input net clearly here, and then the head wall right there, and then you have your head wall just over steepened parts right there. Yeah. And what we can assume is that we have high rockfall frequency and high rockfall volume per frequency event and high snow potential that should give more material to the rock glacier and make it grow more and make it more active. And then we can, this is our same graph as before, just replacing the y-axis with correlation to rock glacier activity growth, or rock glacier activity and the growth of rock glaciers. Basically just saying, the more rock and snow in the system, the more it's going to grow, the more active it's going to be. If we put correlation on our y-axis, we have slope of our head wall down here. Oh, I need to explain one more thing. You may be asking, why did I not just say, look at the slope from 0 to 5, 0 and then 5 to 10, 10 to 15, 15 to 20, all the way up. What that does, this, by looking at the whole input net, it allows you to understand the hydrologic input is if water is actually playing a significant role in water melt and then refreeze in the rock glacier body is playing a significant role in its activity status. And that's why I did greater than or equal to all the way up. This could be done differently, but that's the way I did it, and it works okay. So we have this graph, correlation on our y-axis, slope of head wall here, and volume or production potential of those three things. And if we think these should correlate to rock glacier activity status, we should see that correlation represented probably like that. And here we go. That's pretty cool. That's really cool. So I bring all this data into R and plot it against slope greater than or equal to, and here are my points, and just put a line between them, and we get like that exact curve. It's like pretty great. And we can pull a lot of meaning, maybe too much meaning from this, but I'm gonna do it anyways, and talk about the possible implications of this graph. So let's talk about, what should we talk about first? Let's talk about what it can mean for its hydrologic input method. We go back to the graph before. We're seeing at both ends rockfall and rock volume is going to be probably about 0. And those ends, we see snow falls at the greatest amount, and snow transport potential. If we look over here, we see different correlation values where we think snow and water is playing the greatest role in rock glacier activity status effect. Down here, where our slope is 0, we're looking at the whole rock glacier input net body, and we have very low correlation. That probably means is that total water input to the rock glacier body doesn't mean that much. What does mean a lot is how much snow is being moved into it. Even here, when our sample size is relatively low, and we're looking at just values above 85, we're still having a better correlation than down low here. And that, it's not causation, but it's reason to believe that avalanching and wind transport is having a significant role in recharging these rock glaciers. Now let's look back at the rockfall. We're trying to find this mid-ground and slopes that are not too steep, so they're not failing too infrequently, but not too steep that they're failing in small volumes. And we see that right here. We see this nice mid-ground of like 45 to 65, where we're seeing a high correlation to rock glacier activity status. You may be saying, 0.35 is a pretty horrible correlation value. Yeah, it's not great. It's way better than 0.07, which is our insolation correlation value, and way better than the after correlation value. And the thing is, I'm doing numeric correlation tests on just 3 categories. Extinct is 1, intact is 2, and active is 3. So a numeric correlation with 3 different categories is pretty rough. Like it's not going to return good values no matter what. You could do clumping methods on this, but most of the papers in the current literature is focusing on correlation values and p-value tests, which I'll get into those. As I said, this isn't that great, right? That's still pretty low. Let's try and do better. It seems like these large areas of steep terrain are doing a good job at supplying rock and snow to the rock glacier. But how does this input area affect the output of the rock glacier body? So if we think about the input net as an accumulation zone of the glacier, and the output, which is the rock glacier body, we really need to start thinking of how well fed these features are. So looking at how much area is feeding the feature. We can do that by 2 ways. We can compare the input net size, meters squared, to the rock glacier body, and meters squared looking at area. But what we're really trying to understand is how the area of the input net affects the volume produced by the rock glacier. So I came up with this wonderful unit of square meters per degrees. And what I'm trying to say is that if you have a feature flowing over a steeper slope, it's going to have normal faulting and be extended and pulled apart, and its volume should be less than the same feature of the same area flowing over a flatter slope, or even hitting a slope that turns a 0-degree slope. We're going to have reverse thrust faulting to compress the feature and create a relatively higher volume. So we can divide the rock glacier superficial area by its average slope angle to get a better proxy for volume. We do these tests and we bring it back in R. Here we go. It's slightly better. It's not that great. But here is our original, where it's just a mountain area above a certain degree slope compared to activity status. And then here is it by meters squared, it should be meters squared. And then here's it by its proxy for volume. That's pretty cool. We're seeing that at the slope above 45 degrees is well correlated to activity status. Its correlation is 0.375, and its p-value is that number. And as long as your p-value is below 0.05, it means your result is statistically significant. And that's way below it. So it's quite closely related to activity status, even though we're doing correlation calculations with just 3, which is like bad. And we're still getting pretty good returns of 0.375. That's like not too bad. Do I want to go? No, I don't want to go there. So, what we can then do is take our most correlated slope attribute and bring it over here. And this graph is kind of crazy for implications, and we're going to unpack this all in a bit. I also did a correlation grid in the background and a ton of R data processing and whatnot, and I found that the RGNet mean elevation had a correlation value higher than the actual rock glacier body. And this kind of makes sense. If we're saying that our input nets are highly correlated to our outputs, then the elevation of them should also be correlated. And we're probably getting that higher correlation because it's sourcing snow from higher up, higher snowpack, more avalanching, and more input. And then what I've done is I've taken this data set, which is my highest correlation value based off this plot, and plot against my second most correlated attribute, and we get this graph. let's just look at it. Like that's cool. Really cool. What this is effectively doing is showing the ratio of steep input area to output volume required to sustain a rock glacier at varying temperatures on a local scale. You're saying, where are you getting temperatures from? Your mean elevation is essentially a temperature. In a local sense, across Taylor Park, your mean annual air temperature is going to be just controlled by elevation. Sure, if you went to the Wasatch or the Sierra Nevada, the elevations won't be as correlated to air temperature between Taylor Park and there, but within Taylor Park, elevation's essentially temperature. So what we have here is temperature, and here we have input amount. What this means is that as climate warms, you're going to see these zones shift upwards, meaning you're going to require a greater amount of input, either through rockfall or snowfall, into the rock glacier body to sustain activity at a lower elevation. These have long been done for glaciers, comparing snowpack to average temperature and seeing that happy median where they seem to grow. This has never been done for rock glaciers. From what I can tell, this is probably the best way of modeling the regression, using geospatial attributes alone. No climate data, no nothing, just looking at the landscape form. And what this is saying, from a land management standpoint, if you want to understand which waters can be there the longest, we now have a way of differentiating that much more clearly. You have these active ones up here, and especially this one. That's very far from that transition line. It's going to stay active for a long time because it's very well fed. That's what I mean. Well fed. The amount of food it's getting for how much it's building is quite high. It's going to keep going for a while. These ones here, even though they're higher elevation, they're probably going to die sooner because they're fed poorly. And that's going against a lot of what people are currently thinking right now. And the applications for this are quite expansive. You can use this for resource management. Like you could use this right now, go up in Taylor and tell which basins are going to be wetter longer and plant forests based off that, and regenerative logging. Like, this is incredibly useful. It's also useful on Mars because we can't go to Mars, obviously. So we can't differentiate between active, intact, and extinct. What we can do is measure input at size, steepness, and area. And we can do that for Mars, put it on this graph, and understand which rock glaciers were active the longest. The implication this have is that it could tell us on Mars or other planets, because Mars isn't going to have many different climates, which apparently Dave just told me. You could tell which areas are wettest the longest and tell paleoclimate data about Mars through rock glaciers. People have questions on this. This makes sense. Cool. And this is ignoring, as I said, the climate lithology, but we're assuming that over our small study area at Taylor Park, that it's relatively constant. So, what other work has been done around this? Not too much. There's a master's thesis talking about rock glacier length related to the mean headwall steepness, and they didn't find any correlation. Their sample size is much larger, but they visited only one rock glacier in the field, and their study is focusing on mean steepness of headwall, and my study has also corroborated that, agreeing that the mean steepness of headwall and the total input net size doesn't really mean much for a rock glacier, and you can see that on my graph right here. Basically, this whole master's thesis was focused right here. They're just looking at the whole input net size, not just the parts of it that matter. They're looking at means and transects, they're not looking at sums. And then there's another paper in Switzerland looking at headwall area to rock glacier growth, but they're only looking at active rock glaciers and not trying to differentiate between ice content and activity status. They also looked at surface velocities. And there's also some papers out of Greenland looking at headwall recession rates, but neither have looked at amount of steep slope or the relationship of headwall size or steepness to activity status. So conclusion. Within Taylor Park, the geospatial characteristics of rock glacier input nets are the greatest known controlling factor upon rock glacier distribution and activity status, and rock glaciers are a reflection of their input nets rather than a reflection of environmental degradational factors. Essentially most of the current literature is looking at rock glaciers from their environmental degradational factor standpoint, looking at air temp, looking at elevation, looking at insulation, how much they're being heated and how much mass they're losing. My whole study has not been looking at that. It's been looking at how much mass is going into the systems and how these things are being recharged. And what I'm trying to show is that it doesn't really matter the output, it matters the input more. Future work. So this whole study was just in Taylor Park. they're pretty cool results, but they're not significant because it's so constrained geographically. We need to do this in other places, other areas. And then investigate all the things that can affect rock fall, lithology, rock strength, and ideal slope angle by lithology. And then snow depth, water, more climate data. Basically add in those things to my slope model. Here's some references, but that's not too fun. So, back to that image where I got the idea. I was like standing right there. Here's a rock glacier. It's about 1,000 feet higher than this one. It's flowing northeast. This one's flowing southwest. All the published papers would say that this one's going to survive longer because it's going northwest, northeast, and is fed, or not fed, that's what I'm trying to say. It's going northeast, it's higher up. What I'm trying to argue is that this rock glacier, I'm not trying to argue, what I've shown is that the size of the head wall is supplying this rock glacier with more mass at a higher rate than this head wall, which will keep it longer in a warming climate, longer than this one would. And if elevation seems to be working, if we're looking at aspect, which is the other factor that other papers have been looking at as a controlling factor, if we think about those papers, they're saying north and northeast aspects are controlling rock glacier growth. And what I really think, if you think about aspect in a more paleoclimatic sense, where is it? I have this written down. Doesn't matter. Over time, your north and northeast slopes will be glaciated more because they are colder, which will oversteepen the head walls. And I'm arguing that even in the studies that are aspect controlled, or I'm not even arguing, I'm hypothesizing that in the studies that are looking at aspect controlled rock glacier mountain ranges, they're not aspect controlled, they're slope controlled because the northeast aspect was most heavily glaciated, mostly oversteepened, and providing the cirque head wall, input net, right conditions to produce these things. So, yeah, that makes sense? That's good. Any questions? It all makes sense. Awesome.
We're a little over before, so if you have questions, you can ask them. If you need to take off, you can take off.
On your graph, cause for the lack of, or it looks like the lack of, how the transitionals look so random?
Yeah. Because it's the transition. You're having both in there. It's kind of hard to tell what's intact because it's like moving maybe a little bit.
If you were to add something, another data value before the initial round loaded,
What?
can you add anything to the or anything?
This is all preliminary.
I got lots of questions.
Ask me away.
Here we go. Let's go.
So, what would be an easy way to check your activity status?
Field survey.
Yeah, so survey it.
You can look at
And
INSAR as
you
well.
could actually get velocity.
You can get INSAR. That's like future work.
Would having velocity improve correlation?
Should. That was, yeah.
And then the other thing is, like, how old, like, the papers that have dated these things, how old are they? How old are rock glaciers?
8,000?
Yeah, how long have they been active? Were they active at one point, and then became inactive, and then became active again?
You don't know. But likely not completely, they would never go from completely active to completely extinct. They may go from active to intact to reactive.
Right. Because it seems like,
I mean, like a whole rock glacier cycle is restarting at LGM. So you're wiping everything clean at 20,000 years ago.
right,
And you're repopulating it since then.
right.
But you need them glaciers to recede high enough up to expose steep head walls. So,
Right. But I mean, like, so you could retreat a glacier up 15,000 years ago and then put a rock carapace on it, transition it to a rock glacier.
yeah.
And then that's been active since then. Or you could have glaciers retreat away at 15,000 years ago, and then you have a rock glacier form 2,000 years ago.
Yeah, that's cool.
Right? And you're seeing both of those as active,
Yeah.
even though one is really from 15,000 years ago and one is 2,000 years old.
Mm-hmm. From
So-
a water resource standpoint, that's kind of okay.
Yeah, from water reef, yeah, that's
Yeah.
fine. But like, I think that stresses sort of the importance of what you're doing, that you're sort of taking this out of climatic
Yeah.
parameters, is that the climate is very different 15,000 years ago
Mm-hmm.
than it was 2,000 years ago. And even 8,000 years ago. We always think that like, oh, Ice Age is one climate and we're in a different climate now. But in reality,
It's-
right, the climate has changed significantly between 15,000 years ago and now. And most importantly, the insolation, right, that we get in the summer has changed a lot.
Yeah.
Right? The peak insolation was 10,000 years ago. The insolation we have right now in the summer is almost identical to what it was 15 or 16,000 years ago.
Mhm.
Right? And so insulation plays some role.
Yeah, definitely does. But
Right.
to modern activity status is not correlative. But I'm sure it plays a role in their development, 100%.
Right, especially if that development
Occurred
is-
10,000 years
is
ago.
over, yeah,
Yeah.
right?
But
So
I would-
that's what, like, how fast these things move and how fast the rock fall occurs. So the other thing to date is.
Head walls.
You take the head wall.
Date the head walls,
Right,
the
yeah.
Schmidt hammer, date the head walls.
Yeah, and just like how old is the mean
Yeah.
piece of meter by meter square head wall rock?
That'd be really cool to add to this. Yeah,
We need a fortune.
we need a fortune. We need a crane lift in these circs.
Right.
Can we get funding for that?
Sawyer, you got it.
Yeah.
It goes.
I'm a pretty low standard.
What do you think?
Self-preservation.
Did I fail you, Dave?
What?
Did you like it?